So now we have a second way of determining the stability of a 1D nonlinear function, which is to make this new graph the vector field plot of x prime against x. And then look, whatever this is, we just look for the places where it crosses, and then we look for the slope of the function at those equilibrium points. Now, going back to calculus, you remember what that slope is. If the function is called f, and this is the point x0, and let's say this is the point x1, then the slope of the function at x0 is equal to the slope of the tangent at x0, and that is the slope is equal to the derivative dx prime dx, or df dx if you prefer. This is the slope evaluated at the point x0, or again at the point x1. And so we simply take the derivative of this function with respect to x. So dx prime dx, by the way, is not the second derivative x prime prime, because x prime is dx dt, and now we're taking the derivative of that with respect to x. So that is not a second derivative. This is dx prime dx. So let's do this for the logistic. So the logistic is, of course, x prime equals bx times 1 minus x over k. Now, for taking derivative purposes, I'm going to multiply this out because it's going to make it, I don't have to use the product rule. I'm going to multiply this out to bx minus bx squared over k. And now I want to know dx prime dx. And that's easy. We have two terms. The derivative of bx with respect to x is b. The derivative of minus bx squared over k with respect to x is minus 2bx over k. So that's the derivative anywhere. But now we are talking specifically about the logistic equation. And the logistic equation, you recall, looked like that. And this is x equals 0, and this is x equals k. And so to determine the stability of these points, we just plug x equals 0 and then x equals k into the expression for dx prime dx. So let's do it. Let's plug x equals 0 into this, and we get b minus 0. b minus 0 is b, which is greater than 0, so the slope is positive. We just confirmed algebraically what our eye tells us, which is that the slope there is positive. Now, on the other hand, if I plug x equals k into this, then that cancels out. And I now have b minus 2b, which is always less than 0, which is telling me that the slope here is negative, which is confirming algebraically what our eyeball look told us, which is that the slope there is negative. So now we have a general criterion for finding the stability of equilibrium points which is find, given x prime, find dx prime dx, substitute the various points for which x prime equals 0, and ask if this slope is positive or negative. If it's positive, that's an unstable equilibrium point. If it's negative, that's a stable equilibrium point. And this is so important, it has a name. This is called the principle of linearization near an equilibrium point. And so it's telling us that we can find the stability of the equilibrium point by finding the linear approximation, which is dx prime dx, taking the slope of that linear approximation, knowing that the slope of the linear approximation is the same as the slope of the curve, and therefore being able to conclude whether it is a stable or unstable equilibrium point just from the algebra. So now let's do another example of this, which is a little hairier, but you're going to see the principle, which is the principle that we take the derivative of the vector field to linearize the vector field. We evaluate that at the equilibrium points. We conclude the stability. So let's look at that Allee effect again. And you recall what it was. It starts out looking just like the logistic, but then there's that threshold, which is x over a minus 1. And this obviously multiplies out to a cubic. And we definitely don't want to have to deal with that, except we're going to have to deal with that in a minute. So now we want to redo what I just did graphically. We want to redo it algebraically. And we cover the same answer. So just to remind you, the graphical, here is state space. There's an equilibrium point at 0. There's an equilibrium point at A. There's an equilibrium point at K. The overall function looks like that. And we deduced stable, unstable, stable. And now I want to recover that using algebra. So now we have to differentiate. In order to do that, to apply the principle of linearization, we have to differentiate that right-hand expression with respect to x. And this is now going to get ugly because this is a product of 3 terms. We either have to use the product rule twice, or we have to multiply the thing out and look at it as a polynomial. I'm going to multiply the thing out and look at it as a polynomial. And when you do all of this multiplication, I did it offline, the answer is the product of these 3 terms is equal to bx squared over a minus bx cubed over ak minus bx plus bx squared over k. Those are the 4 terms that you get by multiplying all of this out. Now, I'm sorry, that's not dx prime dx, that's x prime. That's just multiplying that out. So that's x prime. Now we need to find dx prime dx. And so we start differentiating. Bx squared over a is 2bx over a minus 3bx squared over ak minus b plus 2bx over k. That's dx prime dx. Now, we just substitute x equals 0, x equals a, and x equals k. So let's do it. X equals 0 implies dx prime dx. This is 0, this is 0, this is 0. This is the only non-zero term. It's minus b. Is minus b positive or negative? It's negative, because that's a birth rate, and b has got to be positive, so minus b has got to be negative. So now we have a negative slope, and so this equilibrium point must be stable. Let's do x equals a. Implies dx prime dx equals. Now we start plugging in a. So this is 2b minus 3ba squared over ak, which is 3ba over k, minus b plus 2ba over k. So 2b minus b is b, and minus 3ba over k plus 2ba over k is equal to minus ba over k. And since a is less than k, a over k is less than 1, so this is b minus b times something less than 1. So this is going to be greater than 0, so the slope is positive, so it's unstable. So the third equilibrium point, which is x equals k, is going to give us dx prime dx at x equals k. Let's substitute k in there, and we get dx prime dx at x equals k equals 2bk over a minus 3bk squared over ak minus b plus 2bk over k. So, let's do some canceling. Minus b plus 2b is positive. It's b. (2bk over a minus 3bk over a is minus bk over a. But so this is now b times 1 minus k over a. Is that right? Yes, it is. This is b times k over a minus b is times plus 1b is b times 1 minus k over a. Since k is bigger than a, this is bigger than 1. This is now negative. This is less than 0. And so x equals k is stable. So we have now found stable, unstable, stable for the 3 equilibrium points by taking the derivative of the vector field and plugging in the values of the 3 equilibrium points, and then simply asking whether that derivative was positive or negative, is to determine whether the slope is positive or negative, and then we were able to infer the stability of the corresponding equilibrium points by the principle of linearization.